All right, let's get right into it. Deep inside every single device you use, there's this microscopic manager, and it is working unbelievably hard to make everything you do feel totally seamless. We call it the CPU scheduler, and honestly, without it, computers as we know them just wouldn't work. So today, we are pulling back the curtain on this incredible, unsung hero of computing.
I mean, just think about what you're doing right now. You've probably got a web browser open, maybe some music playing in the background, a bunch of tabs, notifications, all of it. But your computer, even a powerful one, only has a few brains, a few processing cores. So how in the world is it juggling all of that at once? Well, I promise you, it's not magic. It's just really, really smart management.
So here's the core challenge, right? A single CPU core can only do one single thing at any given microsecond. That's it, one thing. But we ask it to do hundreds of things. This creates this massive logistical puzzle that your operating system has to solve, literally thousands of times a second.
Now here's the key insight. Programs don't just run non-stop. They actually work in these short, intense bursts of pure calculation. That's what we call a CPU burst. And then they stop. They have to wait for something, maybe for you to type something or for a file to download. That's called an I/O burst. And those little moments of waiting, that's the golden opportunity. That's the moment the CPU can switch to doing something else.
So who's in charge of all this switching? Who's the one making the calls? Well, that is the job of the CPU scheduler. You can think of it like an air traffic controller for data. Or maybe even better, like a master chef in a super busy kitchen, constantly looking at all the orders coming in and deciding which one to cook next to keep everything moving and all the customers happy.
So to put it a little more formally, the scheduler is the part of your operating system that looks at this big line of all the programs that are ready and waiting to run. We call that line the ready queue. And it picks one, just one, to give the CPU to. It is the ultimate decision maker.
And yeah, this diagram shows you just how wild that world can get. You can see all the processes just lining up in that ready queue. The scheduler, our traffic cop, picks one and sends it off to the CPU. But then, if that process needs to wait for something, say, your hard drive, it gets shunted over to a different waiting queue. And that frees up the CPU for the next process in line. It's this constant, incredible flow of traffic management.
Okay, but how? How does the scheduler actually choose which process gets to go next? This is the most important part, because there's no single right way to do it. Different scheduling strategies or algorithms are kind of like different management philosophies, and each one has its own set of strengths and weaknesses. So let's look at a couple of the big ones.
All right, the most obvious strategy is just first come, first served. Like a line at the bank. Whatever program shows up first gets the CPU first. It's simple. It's fair in a way, right? But it has a huge, massive potential flaw.
Just look at this scenario. Process 1, or P1, is this big, long job that takes 24 milliseconds. Tucked in right behind it are two super short jobs, P2 and P3, that only need 3 milliseconds each. But because P1 got there first, P2 has to wait the entire 24 milliseconds just to start, and P3 has to wait even longer. This means one single long job can totally jam up the whole system for all the little guys behind it. This is a nightmare for making a computer feel fast and responsive.
This problem has a name. It's called the convoy effect. And just look at the difference it makes. When that long job goes first, the average wait time for everyone is a painful 17 milliseconds. But if we had just let the two short jobs sneak past and go first, the average wait time plummets down to just 3 milliseconds. So yeah, the order, it matters a lot.
And that idea leads us directly to a much smarter strategy: shortest job first. The logic here is beautiful in its simplicity. Just always pick the job that needs the least amount of CPU time. It's actually been proven to be the absolute optimal way to schedule things if your goal is to have the lowest possible average waiting time.
The reason it works so well is just some simple math. When you let a short job cut in line, you reduce its waiting time by a lot. And yeah, you increase the waiting time for the big job behind it, but only by a little. So when you average it all out across all the jobs, it's a huge net win for efficiency.
But here it is, the million-dollar question. This whole shortest job first thing sounds absolutely perfect, right? But it depends on being able to see the future. How can the operating system possibly know ahead of time how long a program is going to need the CPU for? The short answer is, it can't. Not really. It has to guess.
So this brings us to a bigger question. To even compare these different strategies, we need some way to keep score. What actually makes a schedule good? And what you're about to see is that you can't have everything. It's always a game of trade-offs, of balancing different competing priorities.
So here's our scorecard. We want to keep the CPU as busy as possible, right? No wasted cycles. We want to finish as many jobs as we can in a given time. That's throughput. And of course, we want to minimize all the waiting around. But look at that last one, response time. This is crucial for us humans. We don't just care when a program is done. We care about how quickly it starts responding to us. That initial feedback is what makes a system feel fast.
And let's just go back to that first come, first served convoy for a second. This chart just hammers the point home. Look at that difference. The choice of scheduling algorithm isn't some tiny academic optimization. It has a massive, measurable, real-world impact on performance.
But it's not all just about raw numbers. What about fairness? Think about it. A strategy like shortest job first could be optimal on paper, but it could also let a really long, important process starve, just waiting forever because little jobs keep cutting in line. So sometimes you have to sacrifice a little bit of pure efficiency just to make sure everyone gets a fair turn.
So with all these different strategies and competing goals, how does your computer actually do it? Well, modern operating systems have one final, absolutely brilliant trick up their sleeve. It's a real game changer. It's the power to interrupt.
And that trick is called preemption. This is the superpower of the operating system, to just stop a running program in its tracks, pause it, and hand the CPU over to someone else who needs it more. It doesn't have to wait for the program to finish or take a break. It can just butt in anytime.
And this visualizes it perfectly. Look at the left, the non-preemptive way. Process 1 starts and it gets to run for its full time, no interruptions. But now look at the right, the preemptive world. P1 starts running, but then a shorter job, P2, arrives. The scheduler sees this, immediately preempts P1, pauses it, and lets the short P2 run to completion. Then it goes back and lets P1 finish. This is exactly what makes your computer feel so snappy and responsive.
And I want to be clear, this isn't just some abstract theory. This is the absolute foundation of every modern operating system you use every day. Windows, Mac OS, Linux, you name it. That feeling of being able to click on a new window and have it pop up instantly, even while a huge file is downloading, that's all thanks to preemptive scheduling.
So the next time you're juggling a dozen different apps, editing a video, browsing the web, listening to music, all at the same time, just take a second and remember that invisible hero working deep inside your machine, the CPU scheduler. It's the silent, lightning-fast manager that transforms a single-minded processor into the masterful multitasker you use every single day.